So this class is in bioengineering, it's 280A, and in double E, it's 20. Who knows what 207. That's what it is in double E. So you should be registered in either one of those classes. Welcome, and if you're new to UCSD, welcome to UCSD. Dr. Liu and I have given this course now for, I guess, about 8 years, something like that. It's evolved over that time a little bit, but it's sort of hitting a steady state, as it were. And the general idea is that at the end of this, you will be able to analyze images in terms of their quality and the speed with which they are obtained and the physics behind making them and things like that. The two examples we're going to use for this class are computed tomography will be the first half of the class, and then magnetic resonance imaging will be the last half of the class. And we divide it up that I do CT and Dr. Liu does MRI. Both of us have been doing research in MRI since the late 80s. No, not Tom. Sorry, that's me. Tom, probably late 90s. I don't know when he started. He's younger than me. So I've seen a lot of changes in both MRI and CT. The remarkable thing about both these fields is as soon as you feel, oh, what else can be done? There's no other innovations that can happen here because we've, done the best you can do. It'll change again. So CT in particular recently has undergone these massive changes. So, but the concepts we're going to look at in this course are more general, and they will go across other imaging modalities like ultrasound, nuclear medicine, the photographs you can take with your ridiculous camera you have in your pocket right now, right? So you pull out, like I can take a picture of you guys, I won't for whatever reason, but take a picture. That picture is 8,000 pixels by 6,000 pixels, right? It's phenomenally huge compared to what I've grown up with as medical images. For example, most MRI images are 256 pixels by 256 pixels, and they look great, but they're tiny compared to what that computer in your pocket can do now. And some of the cool things that imaging device in your pocket, I mean, if you use Google Images or something, you can say, oh, find this, like, you tell me what should be deleted in this picture, and it takes out the stop signs and this and just like segments it instantly and then removes them by interpolating across that beautifully. You're like, oh, okay. So imaging is everywhere now, and the methods, the underlying engineering of how you process pictures is essentially what we want you to get out of this course. There's 2 lectures a week. As you know, it's from 11 to 12:20, I think, on Mondays and Wednesdays. Both Dr. Liu and I will put our office hours immediately after the lecture. Okay, so we'll stick around. If you have questions, you stick around, and then we'll do our office hours there. Because our labs are in disparate locations, and so it's easiest for us just to stay here for the office hours. And it seems to have worked thus far. The lectures, will give a real-time lecture. It is highly correlated, if not identical, to lectures that have been given in the past, okay? And so those lectures are online, so you can watch a lecture before you come here and see the new one, right? And I don't have a script or anything, so they change a little bit. I wander around a bit here and there, so they will change, but the fundamental concepts are going to be the same. And so we have I forget where the link is. It's on here somewhere that there's recordings of this year's lecture. So if you missed the lecture for this year, the recording will be up right afterwards, like within an hour or something. And so I think that's going to be at this link here. And the advantage of using that method is that you can watch the lecture in like 1.25, 1.5, 1.75 time. And then it's like I'm jacked up on amphetamines. I'm just talking really fast like this and going and going and going. You get exactly the same amount of information, but just in like half the time, right? And you get used to it. Like, I don't know about you guys, but I get used to it. I always speed these things up. And then specifically for me, if you then go back to real time, it's like I've been drinking quite heavily and I'm really talking slowly like this. It's bizarre, right? Your brain goes into this fast gear, and then when you go back to normal mode, you're like, oh my God, what kind of species are we? We're like communicating at 5 baud, by going blah, 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 right? So you can imagine if an alien species ever comes here, they are not going to be using sound to communicate. Not a chance, right? They're going to be using electromagnetic radiation between organisms so that they can communicate at the speed of light, right? There's one organism here on Earth that, does communicate with electromagnetic radiation. Do you know what it is? It has a one-word vocabulary, which is buzz off. It's an electric eel. Just goes boop, and this pulse comes out, right? And that's its word. It's like buzz off, if you're a polite person. So there is a required text for this, and I recommend for those of you who are like, oh, should I take this course? Do I have enough math to do this course? Read this textbook, parts of it, the stuff that we're going to do today, and an image quality, and that'll tell you where the level is. This is by a friend of mine at Hopkins. We work together. Jerry Prince wrote this, and he's exceptionally good and detailed, but very mathematical, so kind of algebraic, right? And so the level of math is in those chapters, and so just sift through that. If you're like, what the heck is this? Then you might need some remedial help. If you're just like, oh yeah, I know what that is, then you're good. There's some other supplementary texts, which one is by Dwight Nishimura. You can get online for about $30. It's a great little introduction to magnetic resonance imaging. It's been around for about 30 years, something like that. And then there's another text, which I'll talk about later, which is a big medical physics text. Okay, so I think this is the link here that, let's just click it, see what happens, that will take you to all the lectures from years past, right? So if you go up here to playlists, this gives you, 21 lectures, 22 lectures, 23 lectures, all that, and then extra videos on sort of side sessions on linear systems or whatever. So that's a really cool resource that we have there. And so if you want to read up before coming to the lecture, such that you're loaded with really good questions, that would be great. The grading, class participation, Dr. Liu is really good at using either Canvas or other systems for getting interactive things going. So he will do that a lot. I will not. And, so that'll be sort of the class participation part there. And then we've got homeworks that you'll hand in. There's I think 6 total homeworks, something like that, over the course of the 10 weeks. And the big thing is the 2 projects. And we're going to ask you to either explain some part of medical imaging, some topic that you're interested in. There'll be example topics given to you, and example presentations from years past of really good projects. The projects that we find most interesting to listen to and watch are the ones that actually use either Python or MATLAB to simulate something. So you build a simulation of some kind of imaging process, you tweak with those parameters and show how it affects the quality of the image, the speed, or et cetera. And so that requires a knowledge of Python or MATLAB. MATLAB is required to do some of the homeworks, right? If you have never done MATLAB, that is absolutely not a problem, okay? Because now, every year it gets better and better, and now Claude is out all of these large language models, or ChatGPT-4. You can just speak to those in English, and they will produce beautiful MATLAB code for you. And we have no problem with that. Okay, you can create code using a large language model, no problem. If you have MATLAB experience and you say, gosh, I spent like 3 years getting really good at MATLAB, why did I do that? I'm now displaced by a robot. That's your experience is still valuable, because sometimes the robot will be wrong. The robot will do something goofy. and you look at the output, and for you to figure out what it is, you have to have some knowledge, right, about where the code is going wrong. And but one of the great things is then you look at the code and you go, oh, with my MATLAB experience, I know my problem's somewhere in here. And usually MATLAB's pretty good at telling you exactly where the problem is. So you cut that out and you go back to Claude or ChatGPT-4 and say, hey, what's going on here? This is bad. Redo it. Bad robot. And then the robot will rewrite it and it'll work. So it's phenomenal. It's changed my life anyway. So that's okay. So those projects are going to make 70% of your grade. We have a lot of people, so there'll be teams. And the way we did it last year, and it seemed to work out okay, was that we divided, say we have 12 teams or something. We take 6 teams, present live in the first half, and 6 teams make a video, right? And so we can watch the video of their project, right? And then those teams switch for the second half, and the ones who made a video now are live on project 2, and the ones who were live are now make a video on project 2. And that seemed to work great. We're all good now in making videos. Since COVID changed a lot, right? It changed many things, but one of the things it did was like all this Zoom business and making videos have become essentially trivial. Okay, is there anything else that I have forgotten here? Any questions thus far? Yes. Oh yeah. So the question is the most recent textbook necessary, or is an older textbook okay for this? Yes. For the prints and links, thanks. This is a good question for other reasons. The prints and links thing will be available through this ByteWave course materials. And so you are by default, when you register for the course, you get access to that, but you pay for it, right? If you don't want it, if you don't want to pay for it, you can opt out, but you have to do that within October 12th. Thank you very much, Katie. Okay, October 12th, you opt out, and then you don't have to pay for that access to that textbook. The access is like $35, $40, like to get access to the textbook. It's, if you try and buy it new, it's very expensive. I would recommend going and looking for a second-hand copy, and any edition would be fine. Okay, if you find a second-hand copy on Amazon or whatever. That goes for all of the textbooks that are listed here, that any edition is going to be fine. Okay. In fact, I think there's only 2 editions of the Prints and Links textbook. Any other questions? Okay. I'm not sure if Tom has anything he wants to remind me to talk about. There is a course summary calendar down here. It looks a little goofy right now. Some things didn't work right in the import, so we'll spend some time fixing it up. But here we are at September 30th on lecture 1, and then we'll put in the expectation of when the problem sets are due, what lectures and their topics are, and when the projects are going to happen. Okay.
So the calendar should look okay on the student view, though.
Oh, it looks okay on student view? Okay.
Yeah, because they don't see everything we see.
Okay, perfect. Thanks. So Tom says on the student view, your calendar should look pristine. On my view, there's some weird things going on. Okay. Any other questions? Okay, today our goal is just to do an introduction to medical imaging, basically. And it's sort of a motivation as to where we're going and why we're going to need to learn linear systems and learn the Fourier transform and learn all of this kind of stuff, analysis stuff, in order to understand medical imaging better. And if we have time, I'll do a little example of how you can use ChatGPT to write MATLAB code. Okay, I don't know. How many people have done that? Like, put them way up. If you've done yeah. Okay, great. How many people have written MATLAB code? Okay, that's a lot of people. Okay. You're in for a surprise. Those of you who haven't done it, you're just like, what was I thinking? It's pretty amazing. Okay. Okay, if there's no other questions, I guess we can launch straight in here. Do you guys have anything you want to add?
Sure. Using ChatGPT, you will be required to write down the questions you ask it.
Oh, the prompts? Yeah, okay.
This is a little bit of the science behind what you ask it. That's
Yeah.
the thought process. You want to see that you're thinking and not just, like copy paste.
Right, yeah, okay. That's a good point. So yeah, your prompt, which is like 1,000 times shorter than the code. Yeah, you just give us the prompt that you use to generate the code. Okay, we'll look at a quick example of that if you don't know what I'm talking about. But it's great showing it to people for the first time, especially faculty colleagues, and they go, "We're already a meeting, you can do this." And you're just like, watch this. And you type 2 sentences and like 100 lines of Python come out and say, there, look at that. And he was like, what? Yeah, that's great. We laugh, but it will be the end of mankind, I guess, right? That's it. Well, it'll be the end of high-end engineering people other than robots. Just think about that for a minute. It was like, what? So I have little kids. I'm like, what do I tell them they should do with their life? I have no idea, right? I have absolutely no idea. Make good shoes would be one, like out of leather, or like really great gloves. I don't know. Okay. So the video of this particular lecture, you can just, all of the videos are available on YouTube without any protection. They're all out there. So you should be able to just get them. Okay. So this is that other textbook. There was a Nishimura one on MRI. This is a general textbook on the physics of medical imaging. So it's not from the mathematics perspective. Jerry Links comes from the electronic engineering perspective and sort of a signals and system perspective to imaging. This comes from the physics side. And so it's much more meat and potatoes, like practically speaking, how does a CT scanner work, right? So it's a really good book. You can find secondhand copies online sometimes for a great deal, right? On the early, so I've got like 4 copies of this because I go, $20, I gotta buy it. And so I just buy that. So if you're gonna do medical imaging in your future, I would get that book. So here's the goals: basic understanding of physical principles. So in terms of X-ray imaging and MRI, where does the signal, how do you generate the signal in the first place? What's the physics behind generating a signal to make a picture, right? How do you then take that signal and process it to compute the image or the thing that made the signal, right? And then once you've got images, there are certain things that you can use to compare the quality of those pictures, such as the signal to noise, contrast to noise, what's the spatial resolution, etc. And we're all pretty experienced with that now with cameras, right? Because when you're at somebody's, birthday party and they turn out the lights and there's only candles and you use your phone, it has to do some kind of dynamic shifting and the signal to noise in the background gets all grainy and stuff because there just aren't that many photons, et cetera, et cetera. And so a lot of times, if it gets low signal to noise, you have to smooth it. So the spatial resolution, the sharpness of the picture goes down. We're going to look at that in detail. We'll look at some applications of CT and MRI. Usually we'll put one lecture together that's just like straight up clinical applications, what's done with this stuff. And ideally, at the end of this, you'll be able to look at an imaging system and think critically about how it could be improved. What are the features of this imaging system that basically seems to be its limitation, that you can't make the picture better for whatever reason, et cetera. So once I was showing a cardiac MRI. This is very early in the late 80s to some cardiologists who were interested in getting in a cardiac MRI. And I'm showing them the movies at the scanner. And then they look at it and go, oh man, that's great, but can you focus it a bit? Right? And you're like, I can, but it's going to take a lot longer to take the data. But it's okay. So the basic principle, or the basic machine that we're going to look at, we have an object. In this case, it's a cartoon of somebody's brain here. So this is called an axial slice. It's like you take a a cut like this through the brain, you look right at the brain. And so there's obviously different tissues in there and different spaces and bone and all this stuff. So the imaging device is going to measure a signal from this object. The object itself just sitting there doesn't really give off a signal other than like infrared radiation and then reflected optics and stuff like that. What we're going to do is we're going to generate a signal with MRI, or we're going to generate a signal with X-rays with computed tomography. And so that's our imaging device. It creates a raw data set. So this is where we go into the digital data domain. We now have a set of numbers that we have measured from this object. And they are usually arrayed, those numbers are arrayed in some sensible order, right? You know, there's some kind of relationship between the numbers over here and the raw data. As we'll see with MRI, this raw data you collect to, you know, it is the Fourier transform of this picture, which is kind of miraculous, but we'll get there. After you understand the math, it's not that miraculous, but initially it looks miraculous, right? CT, the imaging data is something different. You cast shadows and you record the shadows. And then you take that raw data and apply some reconstruction algorithm. And this is a huge cottage industry. Many people work on reconstruction algorithms, right? That are optimal for, say, the least amount of data. And you get a picture of the object in your scanner. And so here's the actual object, and this is our representation of that object that's come out of the scanner. And remarkable high fidelity pictures of the body now come out of these scanners. It's quite spectacular. Such that when you come to the hospital and you've got something actually wrong with you, and you go through radiology, 90% of the time after you get out of radiology, they know exactly what's going on, right? So it's a huge part of healthcare, right? Is to get you through the process to get the pictures so they can see what's going on, right? The biggest, sort of feature, mathematical feature of all of this is the Fourier transform. And this is Joseph Fourier. He changed human experience, right? This guy. And the way it occurred was he was trying to solve a differential equation, trying to figure out if I have a bar and it's got all temperatures, different temperatures along the position on the bar, say it's touching something really hot and over here it's touching something cold, what's the actual function of temperature along that bar, right? That's the problem he was solving. And he came up with this idea that you could create functions using just sine waves. So you add up different sine waves of different frequencies and you create any function you want. And this became Fourier analysis of the Fourier transform, completely revolutionized engineering and human experience, right? You should, at the end of this course, be able to think in Fourier space. You should be able to look at a pattern and go, what would this be like in Fourier space, right? If it's just a flat picture, what does that look like in Fourier space? If it's something really complex, what does that look like generally in Fourier space? If it's a simple plane wave, what does that look like in Fourier space? Those things, you should be able to do it like that, okay? And we'll have a little library of that. This guy changed everything. Even quantum field theory, if you believe this, like say you want to do quantum field theory and you got to come up with a field that when it's all together looks like a little pulsy thing that's traveling at some speed and it's an electron. To do that, you basically break the field up into these modes and you put the amplitudes of those modes into the Schrodinger equation and out pops this freaking electron. So even in that, Fourier is in there deep inside that stuff. And we'll look at this in detail, but say I have a function that looks like this. It's a square wave. It's just a bunch of top hats like this. And what the Fourier theory says is that I can use a set of sine waves, and all I have to do is define their relative amplitudes. This amplitude is, say, 1, this is a quarter, this is, what are we here? Yeah, amplitude's 4, 4/3, 4/5, right? That's the height. And then in some instances, you got to shift the sine wave back and forth. That's the phase. And you add those up. So this plus this gives you this thing. Then you add this one in, it gives you this thing, and you just keep going, and you can eventually produce this picture, right? So you can either carry this around in your pocket as numbers, that's my function, or you can carry these amplitudes around in your pocket. It's equivalent information, right? And so we're going to get to know this really well. This is the continuous Fourier transform. Here's a image, fxy. These are what are called as Fourier components, right? And if this is my image, the inverse Fourier transform puts the Fourier components in here, and I can create the image by using these as the weights on these phasors to make the picture, okay? This formula here, you are going to know inside out by the end of this, right? You got to be able to use this equation all the time. MRI is this equation, right? The whole thing is this equation. So this space over here is called Fourier space, like the coordinates, K space, frequency space, harmonics, modes. It's got a whole bunch of names, but and when you get to MRI, this will all be K space usually. So history of CT and MR in 1895, Röntgen figures out that some weird ray is coming out of a tube that he's excited with a gas in it, right? And it's making shadows on a fluorescent detector, right? And this is amazing, within like 2.5 years, somebody is using these rays to make medical images, right? So before the turn of the century, like right away, right? Somebody jumped on it and it was making, and they used to have, in World War I, they have a cart or like a wagon with a horse, and it would come around, and when people were injured or they had shrapnel, they had bullets in them and stuff, they would put them in the wagon and find out where it was, try and extract it, right? And that was, at very early on in the 20th century. Halfway through the 20th century, on two coasts at Harvard and Stanford, Bloch and Purcell both discover that the proton will go through a transition. If you put it in a magnetic field, it will go through a transition between two energy states that's dependent on the magnetic field. And normally, if you irradiate it, it's usually with radio frequency energy, you can make this transition occur, right? So if I have a thing of water and you irradiate it with RF energy, and you're in a magnetic field, nothing happens, and then all of a sudden, a lot of the RF energy goes into this water at a certain frequency, and that's the Larmor frequency it's called, and this is a resonance called nuclear magnetic resonance. And pretty quick after that, I don't know, less than 30 years, people like Paul Lauterbur are putting that signal together to make medical images. Okay, so you've got a lot of protons in your body. You can sit in a magnetic field, and so you can get this signal out of the body, right? About the same time, Gregory Hounsfield is at EMI, and he invents CT scanning, in which you take a projection image with X-rays, but then you rotate your X-rays around the object, and you can create a two-dimensional picture, right? And he had a lot of, the EMI at the time was rolling in cash because they owned all of the copyright for the Beatles songs, right? So they had tons of cash, and so he got to play in this laboratory that he designed to play with this imaging thing. So here's a picture. This is old Röntgen. This is a picture of his wife's hand made with this special ray that he did. And unfortunately, the early days of X-ray radiation, and also the early days of sort of radioactivity were fairly lethal to the scientists that were involved, because they didn't really understand the dangers of radioactivity or high energy X-rays. And so they pretty well all died of cancer, right? But they had huge doses, right, over the course of their life. So X-ray imaging, the basic principle is I have a big source. It's like an X-ray light bulb. So instead of, 2300 Kelvin or whatever the light bulbs you get, instead of photons at that temperature coming out, they're coming out as X-rays, right? And so it's an expensive light bulb. To get one. It costs like 10 grand or something like that, or 50 sometimes. But it produces a very bright flash of X-rays here. And so that bright flash is usually, coned down and focused on a target, and it goes through the target and hits a detector screen, and you get a shadow, right? And so this looks like an inverted image, such that what is bright on this image is high absorption of X-rays, okay? And so this is a chest X-ray. It's done millions of times a year in a hospital. If you go in with some kind of respiratory abnormality or, a vascular abnormality, they'll do a chest X-ray. Or if you break a bone, they'll do another type of X-ray. Early X-ray imaging, here you go. Here's the patient. This is the source of X-rays right here. Here's the patient, and the patient is holding the film screen detector right here, nice and close, okay? And this old joker is gonna go put a bunch of X-rays through this and make a picture, right? And so that's early clinical X-ray imaging. This is one of my favorite bad uses of X-ray. This is a very early on Philips. Given their outfits, I'm thinking it's 1930s, 40s. And so in shoe stores, although some of my physics professors when I was an undergrad actually did this when they were kids. So you go to a shoe store and you take the shoes out of the box, put them on your feet, and stick them in this machine. And there's an X-ray source down here and a fluorescent screen right here, and you can look at the bones of your feet as you wiggle your toes, say, oh yeah, these shoes fit great, right? But this poor joker is the shoe salesman. He's there every day, right? Getting X-rays. You as a shoe customer, that's probably fine, right? You're probably okay. But this guy, that's a hard job, okay? So here, this is a modern X-ray system in which you have the X-ray source here, and then the detector is a fairly large cassette. It's a digital cassette that will just measure X-ray incidence, and it can move up and down on the patient. And in this case, see this, he's being offered a drink here. It's not a cocktail. It looks like a milkshake, and it's got barium in it. So it's like this thick, gooey milkshake. And then he's going to drink it. He looks a little concerned. He's like, what is that? And so he drinks it, and then that material absorbs a lot of X-rays because it has barium in it, right? And so it casts a really very strong shadow. And so while he's swallowing this, they take the X-ray tube and they, sort of translate it down and watch the big gulp go down his esophagus. And, so from here to here, and they get a nice movie of the dynamics of the esophagus. Do you have, yeah?
Actually, these are like the fluorescent inside of their blood. Is that the similar strategy?
Oh, okay. So this is a type of contrast agent. Okay, as we'll see, there's a lot of contrast agents used in medical imaging. This type of contrast agent is inside the esophagus. So it's just rolling down into the stomach. It doesn't go actually into the bloodstream. Okay, it just stays in the esophagus. In fact, it's not even an interventional thing because your esophagus is actually, it looks like it's inside, right? But you're basically a tube. And so it's actually outside your body, right? And so that's just the mechanics. We'll see, I'll show an example in a second where you actually inject a contrast agent into somebody's bloodstream and that lights up all the vascular structures. So this is a chest X-ray. Again, billions of these have been performed since Röntgen came up with the discovery. And so here you can see that there's a kind of a cloudy thing here, which means there's a lot of fluid. Probably the airways have collapsed a little. There's a lot of, the tissue air ratio has gone up on this side. And the great thing about humans, in terms of when we're imaging them, is humans are remarkably symmetric, right? Cut them right down the middle, and the left side and the right side are just mirror images of each other, except for the heart and liver, a couple of other things. But your brain is symmetric, eyes, everything. So, which is kind of a bit weird, right? You've got this reflected mirror symmetry. Small genetic changes you can flip and have your heart and everything else mirrored image in the other orientation. Do you ever wonder why we're all oriented the same way? It's totally equivalent to go in the mirror world, right? I don't know. So, however, for radiologists, it's really convenient because you're looking at it and go, huh, that side doesn't look like that side. So you're your own control much of the time. And so you know, oh, there's something different there. So this is evidence of pneumonia in this patient because of that inflammation. This is from 2020, early chest x-rays of patients who show up at the ER with COVID, right? And so you can see the severity of the pneumonia in somebody with COVID, right? Not good. And then the first time I saw CT images, these are CT images of a patient. This is from Wuhan, actually. You know, day 5 into the infection, day 15, day 20. I didn't want any part of this virus. It says like, just give me the shot, right? I don't want to go down this pathway. And so that's, you know, the details of what you can see in CT. But the basic X-ray also is good for the original diagnosis. So here's another use of X-rays. So now we've seen esophagus, chest, you know, in terms of lungs. This is checking for breast cancer in women. So this is called a mammogram. It's usually recommended you get a mammogram 40 or 45, somewhere around there. And this is the original mammogram. And you can see why it's really hard to read this. Like I'm looking for something in here that stands out as a small tumorous lesion, right? So this is I'm looking for a small breast tumor in this picture. And as the radiologist, you stare at it and go, what's different about this than a normal picture? It's hard, right? This is a hard job. I did this for 3 days with somebody, and by the end of it, I was like, oh man, this is a tough job. They read a lot of them, and they're on the fence for a lot of calls. You're just like, if I go positive, you know, if you go positive and it's not positive, the woman gets a biopsy, right? And then it comes back negative and you're like, oh, sorry, you know, like I had to go for the biopsy. So this is a projection through the whole breast. This is tomosynthesis, where you do some shenanigans with the detector and the source to kind of limit the focus into a slice through the breast. And so that takes away some of the overlying structures. And so you can see here a classic spicular sort of structure that has these little tentacles coming off it. And that's just a positive signal right there, right? Yeah. Yeah. Yep. Yep. Yes. 100%. And so there are people who've made their whole career basically CT of the breast, trying to build CT scanners that are customized for breast, right? Geometry. Secondly, women who have high risk genetically, there are reasons that you have high risk to have breast cancer. So if you're in that group, you should probably also go to MR, because the MR is very sensitive to find these lesions. You inject contrast, and the contrast sticks around in the lesions. However, it generates a good number of false positives, right? So there's a downside to this high sensitivity. You're always going to pick up somebody who's positive, but you scoop up a bunch of people who aren't. And we'll look at how you analyze that performance in detail. It's like a traditional statistics question. Like, I have a test. What is my sensitivity? What is my specificity? What is my positive predictive value, negative predictive value? And that's what's used in imaging in the end to decide if the imaging system is worth a damn, right? This is like, does it, perform well under these conditions? The issue also is that the imaging system and the radiologist are a unit, like they work together. Some radiologists are more quote unquote aggressive. They will call things positive more quickly than their neighboring radiologist. And so it makes it difficult to evaluate an imaging system when you have all these different users who have their own different thresholds, right? And so you say, well, if I have imaging system A, let's say this tomosynthesis, and imaging system B, which is my new CT breast scanner, and I want to test which one is better, but you don't have like gold standard data down the line, you just look at the observers. In order to get the data, you have to compensate for this observer problem, like that people tend, to overcall, etc. And so we'll see how you deal with that. This is one of my favorite imaging techniques. This is called a invasive coronary angiogram. And the way this works, it's an X-ray system, much like the one where the guy with the shake. So there's a X-ray source, the patient's lying on a table, and then there's a detector under the patient, and you inject. So the first thing you do is you cut a little hole in their thigh and you insert a catheter into their femoral artery, okay, without having blood go everywhere. So you get that in there, you push it up the femoral artery, this catheter, all the way up. It comes up their aorta, down their back, it goes around the aorta and then comes down towards the heart. And then you manipulate the catheter and stick it straight into a coronary vessel. You have two takeoffs at the root of your aorta. Those two takeoffs, you plug one of them with this catheter, right? And then once you've got it engaged, you inject a contrast agent. And that contrast agent only goes in the coronary vessels, right? And so you get this picture, which basically has a background sort of shadow of the patient. But when you inject the contrast, you get a remarkable shadow in the vessel itself, right? And so you can look at really explicit details in this patient. Let's stop this at a spot. Okay. Like here, you can see that there's a certain amount of contrast in a tube, which is this coronary artery here. And then it gets kind of fades out right there, right? And then it gets thick again, and you have more contrast in that tube. This tells you that vessel has shrunken down to a small diameter, and it basically isn't holding as much contrast, and therefore it's a stenosis. So that's called basically a coronary artery stenosis or lesion. And now this is the discovery phase or the diagnostic phase of this imaging. You say, okay, I've diagnosed you have coronary artery disease. This vessel is narrowed down. Doesn't mean you're going to die tomorrow, right? But the probability of you dying tomorrow just went up, right? So if you're doing Bayesian statistics, just like, well, your prior's gone up. Sorry. And so the question is, like, at that point, do I put a stent in there to open it up, right, and keep it open? Or do I just give the patient the optimal drugs to keep their blood pressure down, right? And give them heavy statins so that their lipids go way down, etc. Right? That's a fascinating topic. That's covered in detail in another course called 280C. Yeah.
Is it losing contrast on the left-hand side? Like it appears like the liquid.
You have to tell me where, when you say left-hand side, you mean that?
Yeah.
Oh, this? Oh, this. Oh, okay. How about, okay, let's go through it. You mean that stuff there? Well, yeah, it's going, you know where it's going? It's going into the root of the aorta, which is here, right? So what's happened is we've put the catheter into the vessel, but it's shaking around a bit. It's not like tight. And so when I inject with high pressure, some of it squirts back out, okay? And then you can see what happens to the stuff that squirts back out is it gets shot up the aorta right away. So let's play it live. Whoosh, like it goes into the aorta, right there and then gets poof, taken out because the part contracts and it gets shot away, right? So that's that. Right? So it is leaking back into the aorta. In fact, if you want to, you can do a diagnostic thing where you have the catheter here and instead of putting it in the coronary, you just goof around and get it into the left ventricle, and then you put a bunch of contrast and you see the left ventricular chamber and you see all the contrast go out, right? And you can diagnose, say you have a small hole between your left ventricle and your right ventricle, you would see a little bit of contrast squirt across the hole, right? So there's a whole bunch of stuff you can do with contrast. Yeah.
Like, I went to a hospital, I saw that people are doing like, X-ray and they actually insert the, HCl into their bloodstream to see at the contrast. To diagnose.
They insert what? I didn't get the,
Hydrochloric.
oh yeah? Well, I mean, here, you can inject this contrast into the LV, see where it goes. If there's a leak, it'll cross. You do it in the atria. Sometimes there's a leak between the atria, it crosses. The other thing is you find that where that leak is, and you can put a little button, right? You have a device, you put another catheter in, and it shoots a device through the hole, and there's a little nitinol device that's basically a cylinder, but then when you pull back your thing, it pops into a button and it fills the hole, right? And so that stops the leak. So that's interventional radiology, and that's done a lot, or interventional cardiology. So we look at computed tomography. 3 different things happen totally independently. Radon discovers mathematically the radon transform, which we'll look at in detail. It's really cool. It's another thing that if I had something to say, when you leave this course, what should you remember? You should remember the Fourier transform and the radon transform. Those are 2 things you should carry with the rest of your life. You can bore people at a cocktail party telling about the radon transform. And but anyway, so this guy comes up with the radon transform, which says, if I have projection, if I have this object and it has sort of intensities, and I make projections through the intensities at different angles, from those projections, take away the object now. Just from those projections, I can reconstruct exactly what that object was, okay? When you look at the math, it's not, to me, it's not intuitive that it works. If you look at the fact that, oh, I've changed, say, 256 by 256 numbers into another set of the same amount of numbers, I should be able to invert those 2 things, right? So we'll take a look at that. So basically, Alan Cormack then published an algorithm for doing CT with the radon transform, and Hounsfield made his first CT images and reinvented the back projection technique for that, because he didn't read either of these papers. So anyway, but he won the Nobel Prize anyway to get that. So quickly, if I have an object here, this rectangle is my object, and it has a couple of parts. It's got a circle in the middle, it's got a background, and then 2 high contrast features inside the circle. And I send an X-ray beam through this object in this direction, and then count, right, the number of X-rays that land on my detector. When I'm here, I'm going to get fewer X-rays on the detector because they get absorbed by this object, right? So along this line, it has to cross all the way through this thing. So I'm going to lose X-rays all the way along here, and I get fewer on my detector than if I just go through the background object. I get, say, this baseline number, and then this, I get fewer X-rays, but the difference is less, okay, because it's a shorter path length, okay? This is from a textbook. For those of you who are really in the know, I guess basically I don't know what this circle is doing here, because it's certainly not changing the number of counts. So it's like, what's the circle there for? This whole thing should be uniform back here. Okay. So if what we do is we take say we estimate the number of X-rays that were lost or absorbed in this pathway and the number that were absorbed in this pathway, and I plot that function along here and project it back down through that space. This is sort of the primary one projection image I get of this two-circle object. I get a background and I get two different stripes that are the width of those objects, right? If I do the same procedure, but I look at the object from this direction with the X-rays, so I project X-rays through this way, put my detector over here, I get a new function. And if I project that function back exactly the same way I did this one, where these two lines cross, where this line and this line cross, I get this bright signal similarly here. So now I've at least put my bright objects in relative positions that are reasonable, right? And that's with two projections. What CT is going to do is going to do 1,000 projections at smaller angles and then reconstruct the details of that object. And how does it make those projections? Well, here's three versions of a CT detector. The first one is the way Hounsfield made his system. He had a source here. It made a beam of X-rays that he picked up with a detector here. And in fact, his system, he only had one detector element, and he just dragged that detector element along as he used the same source. But let's just say we have enough money to build a detector that's many parallel detectors. So all I have to do is take my source, drag it along here, and measure how much X-ray gets through the object. When you have a single source and you don't want to move it, you can accomplish this by just having something that has a fan beam of X-rays. So it's like a light bulb with a fan beam coming out. And then with one pulse, you get all of these measurements simultaneously. So you don't have to do this raster. And then we can go even farther and say, you know what, let's just stack these things one on top of the other. And I can get a two-dimensional image of what's in here with one pulse, right? And so that's the modern geometry of CT detectors now, is this cone beam detector. And with that pulse, you just get a picture, 2D picture of the object. The way it's set up around the patient is I have a X-ray source and an X-ray detector, and then we rotate those together, right? So I'm going to rotate the source and I'm going to rotate the detector such that I'm picking up different projections through the patient. This is what a modern system looks like. The source is in here and the detector's down here. We'll see more details. And the other thing you can do is you can continuously rotate this detector and source while you're pushing the patient continuously through the scanner and just get what's called helical data. So you're getting all of these projections of the patient. The raw data for a detector that has 256 stacked 1,000 element detectors. So if we go back, let's look at our geometry. This thing here, I'm just going to show you the picture of the amount of X-ray absorption detected by a detector with this geometry. And in a human chest, that's what it looks like. So it's rotating because the detector and source are rotating and getting different views around the patient, right? There's 256 pixels in this direction. There's about 1,000 in this direction. And that's the modern CT scanner uses that kind of geometry to pick up all of these projections such that you can make the picture. A couple of things to note is that you get good signal to noise sort of around here, but then when you're looking at the patient from the side, so you have to look all the way through the patient. Let's stop it here. So now I'm looking through the patient's like right arm and going through their chest and then going through their left arm. That's a very long dimension, right? And you can notice basically the signal to noise, or the uncertainty of the number of photons that have gone through there, gets quite high, because many of those photons get absorbed and you're starting to limit the number of photons that hit your detector at all, right? So that's why it gets all sort of hashy and noisy there. This is what a CT scan looked like in the 70s. You know, it looks like a crappy image, right? It's a really terrible picture. However, if there was a small tumor in here, you would not see that tumor with a plain X-ray film. You just couldn't see it, right? There just isn't, because of the projection. You're taking one projection. There just isn't enough contrast. Here, you can see a distortion of the brain, and you know it's in there, right? So even though this took like, an hour to make this picture because they had to raster through all these things, the patient got a ton of dose. It was, way longer and way more expensive than doing a plain film. They kept at it, right? On the surface of it, it looked like a terrible investment, right? Because it just took too long, too much dose, and all this special stuff. But they believed, and so they started with this scanner here, EMI, and produced these images like that took a half hour each or something. Fast forward to 2010, something like that, and you're getting pictures like this of a human brain from a CT scanner, and that is done in about 150 milliseconds, right? So that's the kind of progress of the technology, the speed. It's absolutely terrific. And that is why in 2019, 90 million CT exams were done in the USA, right? Just think about that number for a second. That is a big number compared to the number of people who are in the USA, right? And so it is a heavily used imaging device. And if anyone wants to do this for your project, one of the interesting things that comes up is that for a large portion of the population is probably the primary source of radiation that they get, right? And with 90 million people, that becomes a fairly large population of people, right? And just walking around San Diego and living in your house with your concrete that's giving off radon and all that kind of stuff, you get, these numbers don't mean anything to you in terms of units, but you get about 3 millisieverts of radiation a year, just being alive, just walking outside and that. A CT scan is anywhere from 1 millisievert to 10 millisieverts of radiation. So it's like the background radiation for a year or 2 years, something like that. So it basically is another background radiation, right? For a lot of people. So people started looking at the statistics of like, is this a crisis? Does this cause a lot of cancers? And it's an open question still, right? Because it's very hard to run a model at low dose and get statistics that are reasonable. Yeah.
So most CT and X-ray use X-rays.
Correct.
Right? And what are X-rays?
What are X-rays? We're going to go into great detail about that, but an X-ray is just like a photon. So these light photons are all in our visual spectrum. And as you go down in wavelength and go up in energy, they eventually become X-rays before they become gamma rays, which are even shorter wavelengths, higher energy. Infrared is below our visual, but long wavelengths, but you can feel it at your oven. You can sort of feel them with your hand. It's all electromagnetic radiation. And so X-rays in particular are really good for this kind of imaging because they will principally just go right on through you, right? So basically when you shine a visual light flashlight and you put it on your chest, and if it's bright enough, you'll see a red dot on your back, right? So those photons make their way through your body. But by the time they come out, they've hit so many things and bounced in so many directions or so many interactions that it's just a big blob of light coming out, right? And then you have to turn it off because you get hot, right? X-rays, on the other hand, you can pick an energy such that 50% of them just go straight on through and 50% get absorbed. And so you have this really high resolution shadow, right? And it's principally, bones show up amazing. But the X-ray, unfortunately, when it gets stopped by the tissue, oftentimes it produces some kind of chemical change, right? So it like blasts an electron off something, it can actually cause a double-stranded break in DNA. And that's principally the generation of cancer with X-rays. If you do tests in animals and you ramp the dose up, then you'll generate these genetic problems because you get these double-strand breaks. And that is why when you go for a chest X-ray or you go get something, they always put a big piece of lead over your lap because they don't want to mess with that, right? And have genetic changes that are then in the germline, right? You don't want that, right? So, so here's a whole bunch of applications of X-rays. It's spectacular pictures. And so here's a case, you know, she shows up at the ER with some chest pain, acute chest pain. Now you can get chest pain from a lot of reasons, right? And so they put her in the CT scanner, shoot some contrast in, and in about, I think it was like 1 second of imaging, they see this, which is basically the epithelial layer of her aorta. Her aorta has disassociated from the aorta, right? And it's coming out. So you got to get in there now and fix that, right? Because now your Bayesian probability of dying has gone way up, right? You're like, you don't want to sit down too hard, right? So it's amazing. Like, I got chest pain, boom, we know exactly what we're doing here, and we got to do it fast. So it's used all the time. This one, 2.7 millisieverts of radiation, 700 millisecond scan time for the whole thing, right? So this is why computed tomography from 95 to 2007, look at the increase in usage here. It's spectacular. But again, there's this dose issue. Oh, this is another slide of volume, just the percent type of CT scan that's done and the growth in the imaging. So here's a CT scan of the heart, yeah?
Comes in the right shape. Does X-ray scatter around when it comes and attacks a particular?
Yeah, so the question is, just like a light ray, does an X-ray photon scatter ever? Absolutely, it does. And so if it hits, you know, if it hits a nucleus, it'll scatter one thing. If it hits an electron, it'll scatter off at a lower energy. So now I have an X-ray that comes through, interacts with some kind of electron, may eject that electron out of its shell, and the photon itself will shoot off with lower energy in a different direction. Okay, so the interesting thing there is that photon is essentially absorbed in the eyes of your imaging system, because if it comes at a high angle compared to where the source is, you can filter that one out and just say, I'm not interested in that photon. I'll put it in this grid such that anything at a high angle just gets absorbed. And so all I see is straight back to my source, right? Yeah.
Why do you X-rays instead of gamma rays or like ultraviolet rays? How do you decide to that particular field?
It's a great question. So the question is, why use X-rays instead of gamma rays or ultraviolet or something else? And it's because your transparency of the human body kind of peaks out around X-rays. Gamma rays, I'm sorry, incorrect. The transparency is about 50-50 around X-rays. Whereas if I get up to gamma rays, not many gamma rays interact with you. Most of them just go straight on through, right? And the ones that do interact really cause a problem, like blow stuff up, right? So they use gamma rays to kill cancer cells, right? So they'll use radiation to actually kill cells with a really focused beam, right? But trying to make an image from gamma rays, you can make it because you detect a lot of energy, but it's very low contrast. Most of them come through. They use gamma rays, yes, but it's a different type of imaging. And we do that in 280C. We look at the use of gamma rays. And what you do is you inject a substance that itself produces gamma rays. And so then the patient actually is glowing with gamma rays. So the patient is the source of the gamma rays. So all you have to do is find out where it came from. And it's going to go out of the patient, right? So it's not a shadow, it's an actual source image. That's how gamma rays are used, yeah? It has lower contrast, but what you're actually trying to look at there is where, so the molecule that you put in there that produces the gamma ray, you want to know where it went, is essentially. So it accumulates in different places, and then you just get these bright signals. And yeah, the spatial resolution isn't as good as X-ray imaging by a lot, but you can detect very small amounts of something. So if you have picomolar concentrations of something, you can actually detect it's there, right? So that's in nuclear medicine. So this is a CT image of a heart after contrast injection. Okay, so we time it. So we'll look at, actually take some low dose images while the contrast is being injected, and then take the good shot right when all the contrast is in the heart. And so you can see here, we have the left anterior descending coronary artery. The right coronary artery is going back around the back of the heart. This is the circumflex here. Fantastic three-dimensional structure and volume is obtained in 170 milliseconds. And the basic spatial resolution here is like 1 by 1 by 1 millimeter, right? So I did MR for 30 years, and those numbers are stupid, right? They're just ridiculously high resolution and ridiculously short imaging time. To get 1 by 1 by 1 millimeter voxels with MR here, I would scan the patient all day, right? Literally 6 hours or something to get that kind of resolution. So here we just like, boop, one heartbeat, we're done. So it's a different experience. If you want to look at the best pictures, like these pictures are great, right? The medical imaging pictures just are fantastic to look at. And so just go to the, Siemens, Toshiba, GE, whoever, Philips, go to their websites, say medical imaging, best pictures or something, and you'll see all of these ridiculous images. Okay, we're at 8. When did we stop? 20? Okay, so we got 12 minutes. Okay, thanks. MRI, here are the two dudes who got the Nobel Prize for discovering, MRI. This is the guy who got the Nobel Prize for figuring out how to use that signal to make an image. And this is his first image here. He had 2 test tubes in an area, and got the relative position of those test tubes by using NMR signal and adding gradients while he was reading out the signal. And he did it on his NMR spectrometer. And an NMR spectrometer, usually what you do is you have some chemical composition, and it will give off different frequencies for different hydrogen and carbon and stuff in different parts of the molecule. In order to do that well, you need to have the system at exactly the same field strength everywhere for your sample. And in order to do that, they gave you a set of dials and a set of coils that took the magnetic field and changed it as a function of position in space slightly to compensate for, problems with the main magnetic field. So you could set these dials and then get a perfectly flat, beautifully constant magnetic field over your whole sample. And then you get essentially the spectrum of all of the NMR that's going on in that sample. My hypothesis is that Paul Lauterbur was really bad at adjusting those dials, right? And he got so far off resonance with his linear X or linear Y or one of the linear gradients, and he's just like, oh gosh, why won't this work? And then he looks at the sample and goes, hey, wait a minute. Because if you have this constant gradient on, all of a sudden, you don't have a single spike as your signal. It like spreads out over different frequencies because I've got this gradient on. And you go, huh, if I turn the gradient up, it spreads out twice as much. I can turn the gradient down, it goes like, oh, I'm imaging, right? I know the size of my sample by changing this thing, right? So that's my hypothesis, which is mine, right? You can ask him. I don't know you. can't, I don't think. I think he's dead, yeah, sorry. So this is Raymond Damadian, who also was a big developer of MR imaging in its early days. He was a physician. However, the way he chose to make the pictures didn't work that well, so his pictures were always a little blurry, which he was always mad about. And then here's a system that was built at Aberdeen. With Bill Edelstein, worked at GE. I knew this guy for years, and he was great. But this is my favorite phase of a technology, right? Is that you build this magnet. So you've got these coils with this resistive magnet, and you've got the coils in here, and you've got the graduate student in the scanner, right? It's great. And then here's this graduate student with Peter Mansfield, who also, Peter Mansfield got the Nobel Prize too, right? I think so, yeah, for MR imaging. So the basics are you have a big old cylinder, and the cylinder has superconducting coils wrapped in there, and you get the current in those superconducting coils up to a really high value, and then you close it and then close the lid, and now you've got this basically current running forever, and it's generating this massively high magnetic field. And so you put the patient on a table, put him inside that magnetic field. And in addition, we have radio frequency coils that pulse radio frequency energy into the patient. Then you shut them off and you listen to what comes back from the patient after you've pulsed that. And during that, you dynamically change the magnetic field as a function of position in here using these things called gradient coils. So you pulse those so that you get, say, a linear shift in field across the XY direction, or a linear shift in field across the, up and down AP direction, et cetera. And so that dynamically happens, and you create raw data and make a picture. So this machine here, like, it costs nowadays, I don't know, between $1 and $2 million for just a standard one you get off the shelf, $10 million for one of these crazy things. So this is a 3T system. This is probably the one just over in Tom's lab. Here's one that's at a field strength of 7T, 9.4T. These are special systems that they just made bigger and bigger fields. And the reason I want a bigger field is because the signal is higher. Like, the amplitude of the signal that comes out is higher. The frequency is higher. Certain things occur at higher field strength that give you different contrast. But mostly just raw signals noise is what people are after. 99% of scanners look like this, though, that are in the clinic. They're either 1.5T or 3T. Yeah.
For the bigger field, I can see, like, from the 3T, it's most similar like what we have in the morning hospital. So for example, for the 9.4T, what are people usually using?
Oh, the high field strength really got pushed hard to push, I would say, fMRI to get, because fMRI signal is a very low amplitude signal. Like, the change when you see some part of the brain and the flow changes and it changes the susceptibility, you get a very minor change in signal, a very small change. This is one of the things that I missed. Like, it's one of those great misses, right? We oxygenated this rabbit once. We had it breathe really high oxygen, then really low oxygen, and we measured the change in T1 and T2 of around vessels and stuff like that. And I remember picking up the phone. I was busy writing some other grant on something else, cardiac, and this guy Hal Schwartz from Penn says, "Well, what do the results look like?" And I did it, and I said, "No, the effects there, but it's nothing. It's like 4%. And all of fMRI is built on that 4% signal, right? It was like, oh, missed. Swing and a miss. And so anyway, Sagawa published a paper like a year later showing that. But that's principally why you go to high fields, is to do really cool fMRI. At 1.5T or 3T, you make pictures like this, which are spectacular, right? This is showing essentially the different parameters that cause the signal to change its value in time, are T1 and T2. And then there's obviously just density weighted. So the more protons you have in some place, the higher the signal. And we'll see how you can generate pictures that use these different contrasts to generate the maximum, say, contrast between a lesion and your background, right? So, but the details are pretty spectacular, right? And here's an image of the vessels in the brain, and this was done without injecting a contrast agent. You can imagine if you inject something that changes the MR signal to make it much bigger, you could see vessels. But this one is just, it's just developed by enhancing stuff that flows into a slice. That's it. If it's moving and it's flowing into a slice, it looks bright, and then you stack these together and you get this amazing angiogram without any contrast. And then here's an example. These are exceptionally high resolution images of a person's brain. These blurrier pictures, basically, they are bright where blood flows into the slice, okay? And so if this person had some big defect right here, say, because a vessel was blocked and they had a stroke, then you would see a really big old dark spot right there, right? And so now I've got not only beautiful anatomical detail about what is what in here, I also have functional detail about how much blood flow is there in this voxel, right? So MR is amazing for that. Here's if a patient can hold their breath for, say, 12 heartbeats, such that their chest doesn't move over that time, and you average signal together, and you take their EKG and put all the signal back together in the right places in the R to R interval, you can make movies of somebody's heart contracting, which is pretty amazing. You can see the muscle contraction in the left ventricle. There's vessels up here, coronary vessels. You can see very, subtle motions in other parts, other big vessels. You can, with MR, you can just choose any arbitrary plane you want to make that picture, right? Just by rotating these gradients. And so now we see a long axis view of the left ventricle. So this is the left ventricle, left atrium, right ventricle. This is really robust heart. That person looks like they're doing just great. And then functional MRI, where you image continuously in a volume, and then you stimulate the person with some kind of neural stimulus. And so it can be something as simple as scratching their finger, right? And then you'll see brain activity light up in a certain part of their, cortex that's associated with your fingertip. Or you can go to really complex things like show them a chess situation, right? And they have to look at the chess situation and figure out like what they should do next. And when they did that with I think she was like the 5th ranked player in the world. They did these things where they showed her positions she'd been in before and novel positions and stuff like that. And what lit up in her brain when she was like processing these things was facial recognition. So in some ways you can think like she looked at it and goes, oh, that's a really bad face. It doesn't look good. And then this one was like, oh, that's a good face. Yeah. I've had hundreds of hours of MR, and thus far, for n equals 1, I don't think so. However, they've done double blind experiments where they grow mice up in large magnetic fields for generations, and it doesn't seem to do anything. There is one known risk in MRI, and that is if you have too much contrast agent. It's gadolinium is the metal that's chelated to a big molecule that just gets peed out, the whole thing goes out. But if the gadolinium comes off, it is an analog of calcium, I think, for the cell. So it can get incorporated into cells. And if you have many, many injections of contrast, you can build up that. That was just recently brought to light, maybe 5 years ago. So that is a concern, right? So you don't want to do hundreds of contrast injections. But otherwise, it doesn't seem like there's a long-term thing. The biggest risk with MR is flying metallic projectiles. And I'm not kidding, that's how people die. Like there's, I don't know, 8 fatalities associated with MR, and virtually everyone is somebody gets pinned to a magnet by an oxygen bottle, or some other metallic object gets sucked into the magnet at huge speed and just trauma, right? And so those are the fatalities in MR. You got to respect the magnet. It's always on. Yeah. So, okay, so we'll pick it up there on Wednesday, and I'll be around for a few minutes if you want to talk about something.
I like to see it for a few minutes, if you want to see the homework notebook.
Yeah, is it,
I
so,
sent it to you.
okay, let me just stop this and it'll start recording, or it'll start making that.